Welcome back to System Software. So we are finishing up our section on files. The last couple lectures we learned about the file system as an abstraction, files as an abstraction, and how the file system, the hierarchical file system, emerges in the Unix-style file system. We started talking about Syscalls last time, and today we're going to finish up Syscalls, show you lots of live coding examples of using the file system Syscalls, a variety of them. And you'll use those for the next project, the file system or FS project, which will be assigned next week. So right now it's not available yet, or not next week, on Thursday. So you'll see that on Thursday. I'll introduce it. But today I'm just going to give you the tools you need in order to do the file system project. Questions on the last lecture? We'll do the homework as well, but questions on last lecture, file systems? All right, let's go over the homework. So number one, write a snippet of code using snippet of C code using a system call as described in class and in the readings. Opens a file named hello.c for reading. Any takers on what this might look like? Using a system call. So what is the system call for opening a file for reading, or just opening a file?
Is my phone up there?
This one?
Sorry.
No, it's no problem. Any takers? So what's the system call called? Open, yeah. To open a file, the system call is called open. And where can we find documentation of this on the command line if we forget how to use it? The man pages. And what section of the man page do we use for system calls? Section 2. So we type man to open, and we'll see the documentation of it. And I think they even have examples. Not in this one. They don't have examples. Actually, they do have some. They do have some examples. Okay. And sorry, so let me just get to an example here. So we say open, and then let me keep open the documentation. So how do we use open? We call open, and what do we give it? Which version of open are we going to use? What's the homework asked for? The homework asked for a file named hello.c. So how do we use this system call? What's the argument? What's the first argument to this system call? What's that? What? Hat? Oh, the path. Yeah, right. So what's the path here that we need to put? Hello.c, like this? In quotes. Yeah, it's a string. All right, and if you look at the documentation here, this takes at least 2 arguments. So what goes in the second argument? Okay, so somebody says od underscore read. And so where'd you get that information from? How do you know it's o dot underscore? Is it like this? There's documentation of this. So there was an example in class. If you did the readings, chapter 4, hopefully you did the readings, it goes through all the flags. Would any other flags work here for this question? So it opened for reading. Any other flags? Are there any other options for flags here that we could use? Let's look at the reading. So here's the flags argument. It lists all of them, describes them. Is there any other right answers, or is it just O underscore RD only? What's that? Any of them? What if we did write only? Would that work? Oh, so the question asks for open for reading. So, are there any other flags that are for reading? You do the read and writing one. Yeah, you do the read and writing. And any of these other flags, as you point out, most of these other flags you could also add, and most of them would be for reading as well. All right, so here's our system call. What does it return? What's the return value of the open? Okay, we can. Positive integer, what's that integer mean? Actually, it's a non-zero, non-negative integer, 0 or more, depending on whether you consider 0 positive. What does this integer represent? Yeah. The file descriptor. Yeah, and we'll talk about more of that when we get to processes, but it's just a number that the system records for your program, your running program. It lists out, keeps track of all the open files that you have, assigns each of them a number in a table. All right, are we done? Error checking, yeah, that was like the most important thing of like doing systems programming or really designing reliable systems at all. All right, so what would the error checking look like for this case? Say again? Okay, so we can check if FD equals -1. Where do we see that information? We see it in the return value section on the man page, or the examples in class, or in the reading. The reading will talk about this as well. So you can see that if you, as long as you know the principles of this, that, okay, there's a syscall, there's some interface, I may not remember the exact interface, I know generally what it's supposed to do, I know it's gonna have some error conditions that I need to check. And for the specifics of it, you can look in the man page or look in a manual to see what they are. Okay, how should we handle the error? Let's see, if there's an error here, what do we want to do? Look at exit. Yeah, exit is an easy way to do this. So, whoops. I'm just going to exit one because I forget what the macro is. And you can use pierre to help provide some documentation. And you can put any message in here you like. This will just prefix the error message. All right, are we done? Anything else you need to do at a minimum for the open syscall for opening hello.c? Yeah. Well, it depends on what you're trying to do. So I only asked for open for reading. If you did create, that'd be fine too. If you didn't do it, that'd be fine. That actually kind of leads to question 4. So let's say we do this open call and we get an no-ent error. What might that mean? So first of all, where do we find this information about error codes? In the man page. So in this same man page, right under return value, there's a section called errors. So to find what this error means, we can scroll down, it's in alphabetical order, and we can see here's the no-ent error codes. So what can it mean if you get this error code from open? Yeah, maybe the file doesn't exist. Maybe you give a relative path or an absolute path, and one of the directory components doesn't exist. Yeah. So anyway, the point is I wanted to show you, first of all, make sure that you understand the concept of error checking and know where to look for documentation. You don't have to just like memorize this or know this from scratch. This is all documented for you in the man pages and also in the readings that I gave you to read for last time. Okay, any questions on that? Any questions on answering question 4? Okay, let's say we were running this program in the directory, working directory /temp. What would be the full path of this file? So for working directory is /temp, and then we open hello.c. What's the full path of the file that opens, if one opens? Yeah, /temp/hello. Questions on that? We went over that 2 lectures ago on the relative paths versus absolute paths. All right, and somebody already kind of answered this already, but number 3, how can you change this system call so that it creates the file for you if it doesn't already exist? Yeah, the create or create flag. So again, this would be something you would see in the reading. So there's the create flag, and there are examples. There are examples in here, describes the create flag, or in the man page, under the description of flags. All right, any questions on homework? Okay. All right, let's take attendance. Okay, so let's finish up talking about Syscalls. Let me quickly first review what we talked about last time. Let's just go to the example. So this is what we just talked about in the homework. So this is how you make system calls. You make the call, look at the interface, describe what its inputs and outputs are going to be, and then almost always you're going to need to do some sort of error handling. Any questions on this? All right. So be sure to use the man pages to find the documentation of them, or use the LPI book, the Linux Programming Interface book. Okay. So let's go into the actual system calls that are available for us, so that the common ones that we're going to use, the ones we'll use for our programming project that we'll learn about next time. So the first syscall I'd like to show is the stat system call. So this will give you the same information that the stat program gives you on the command line. So if you remember, I showed you this, I think 2 lectures ago. This is the metadata about the file, and also the inode number as well. So the inode number, remember, is, what's the inode number? Yeah, it's sort of like an address. It's like yeah.
The identification number of a file.
Yeah, so each number is given a unique ID, like social security number or unique driver's license number for each file. And does this inode number store the name of the file? So the name of the file here is files.c. Does this inode number somehow store the name of the file? So if we have the inode number, how could we figure out what the name of the file is? Which table? Yeah. So what's the table that records the mapping between file names and inode numbers? Or where is that information stored? Or what's that file called? What's that? The directory file. Yeah, that's what directories are. Directories are a completely different file. So if I look at stat, the directory file, so this is a file, this is its name, but its full name is this Syscalls file. It's a completely separate file. It's independent from files.c, the actual contents of files.c. The only reason this inode number even has a name is because there's a separate file, this file called Syscalls, that contains the mapping between this files.c and the inode number. This name here, this name instead was just what was given on the command line, I'm pretty sure. So this inode number and the information in the file doesn't store any authoritative information about the name of the file. The name of the file is stored in a completely separate directory, or a completely separate file called a directory file, and that's what this stat syscalls file is. Questions on that? So that was from last week, when we talked about how the hierarchical file system emerges from this Unix file system design. Okay, so this is the first syscall we're going to look at. We're going to look at basically how this stat syscall can be implemented, how we can get all this information about the file. Okay, so the stat syscall, it's documented here in this reading, if you want to look at the reading. But we can also look at the man page. So let's take a look at the man page for stat. And we can see here that it takes a string for the path, just like open did. And we have this parameter here. So what's the data type of this parameter? This is called the stat buff. That's what the name of this parameter is. What's this data type? This is some kind of intro to C stuff, I think. Who learned about structs? You learned about structs, right? For sure, right? Not everyone? Did anyone never learn about structs in C? Okay, just people didn't want to raise their hands. Okay. Yeah, so what's the data type of this? What's that? Struct stat. We have this restrict keyword. Let's not worry about that. So is this data structure, or is this data type struct stat? And that's it? What about this symbol here? What does this mean? It's a pointer. This is actually a pointer to a struct. So important difference, right? I hope you learned about pointers. So we're not passing in a stat buff here. We're not passing in a stat buff structure. We're passing in a pointer to that structure. So why? Why are we passing a pointer here? Let's take a look at the return values of this. So what we're supposed to be getting is we're supposed to be getting this. We're supposed to be getting this structure. So this is struct stat. And if you read through this, this has all the information that was shown here. This has all the metadata about the file. Access times, number of links, change times. This is the data structure that the stat function gives you. But if you look at the function prototype here, the function type, this struct stat is not a return value. What is the return value? What's the return data type? What's the return type of this function? It's an integer, right? And so what does that integer mean? On success, 0 is returned. On error, -1 is returned. So what is the meaning of this return value? Yeah, it's effectively a flag, a Boolean flag. I mean, it's not represented the same way with 1 and 0, but it's just an error flag. That's it. It doesn't actually give you the stat buffer. It doesn't give you this data structure that we want. So how does this return value work? How do we get the stat buffer from this system call? So it's being passed a pointer to one of these structs, but the return value is not the actual data that we want, right? It's not the struct stat buffer. Any thoughts, any guesses how we can get this information? Or how this stat system call is giving us a stat structure? What's that? Yeah. No, the errors, we'll just check the error codes. Okay, let me give you a pointer example here. So this kind of style of C programming is really common in systems programming, and actually lots of C programs. Okay, so let's just do a little pointer review. I'll just make up a function here that takes this. Let's do it this way. Okay, let's see. What does this program return? Let's see if I actually wrote it correctly. But what will this program print out when I run it? What's that?
The address of X.
Okay, so we have one taker, the address of X. Any other thoughts about what it might print out? Yeah. It'll print 1, then 2. Any other thoughts about what it might print? Oops, oh, I didn't. Oh, whoops. I passed in the wrong data type. So someone said 1 then 2. That's what I intended to do, but this program will just print 1 and 1. Let me show you that. Actually, it won't print anything. I got a seg fault. So I meant to press the pointer, and the compiler caught it for me. Now this program, what do you think it'll print out? 1 and 2. Okay, x equals 1 and x equals 2. And I even made a mistake trying to do this live. Okay, so why? Why does it print out 1 then 2? So you can see here, we're printing x twice. We've only ever assigned x to 1, apparently. So why is it 2? Because we've passed this pointer to x into the function, and then the function dereferenced that pointer and modified it. So this is what this program looks like. We've got this variable x. So this is kind of like pointer review. Maybe for some of you this is just review. We have the variable pointer, and we have the variable p. So stepping through this program, when I assign x to 1 in main, and this is actually in main, and this is in f. When I assign x to 1, the memory address associated with x is this store integer binary 1. And then what's the value of PTR? The address of x. So you probably saw that depicted with an arrow, right, pointing to x. And now when I call f, what's the value of p? What is the value that p gets? What's that? It's given the address of x. It's whatever the value of pointer is, PTR is, copied into here. We can depict that with this arrow. And so when I dereference p, that is, I make an assignment that doesn't assign to p, but assigns to the address that p is pointing to, then x will change to 2. Make sense? Kind of classic pointer review. All right, so why am I showing you this? Because it's common in C programming, at least in C systems code, to instead of returning values just with the return value, just with this return instruction, like this, instead we can use parameters as return values. So if you pass a value as a pointer to a C function, it can serve both as an input and an output to the function. Now, in other programming languages, higher level programming languages, this is kind of like bad style, maybe, these days. Although there are older languages where you would actually denote parameters as input and output parameters. And this style is preserved with pass by reference, passing pointers in C. Questions on this? Hopefully this is review, right? I think everyone's seen pointers. So understanding pointers is pretty important for systems and systems programming and systems implementation because they're used frequently. So instead of having this large struct being returned by value as the return value, instead the way this stat program works, or the stat system call works, is you, the user of stat, are expected to first construct this buffer, construct this struct. You have to actually allocate memory for it yourself before you call it, and then you pass a pointer to that memory to the system. And there's all sorts of reasons in the operating system world to do this. So one is for efficiency, so you don't have the operating system creating new memory, spending time doing that when it has to serve lots of other users. It also means that you don't have to have this switch between memory space or kernel space and user space. But for us, if we want to do systems programming in the Unix world, this is what we have to do for many of these. If we ever want to get any information from the kernel, we need to construct this. We need to allocate this memory and construct this struct ahead of time before we make the syscall. And so this is actually the output of stat. So this int is being used as the error output, and this struct is being used as the output if everything goes right. This is in contrast to something like the open function, where the return value is both the error output and also the actual return value, the file descriptor. They just kind of divide up the space of numbers. All right, questions so far on this concept? All right, so to actually use stat, what we're going to do is, let me write it up. Let me hand type this so you can. All right, I'm just going to copy over some boilerplate here. So these are just our headers. I just kind of have some boilerplate headers for I/O and making syscalls. And again, we're going to have a program that, or a program that reads in a single argument, and we save that argument to the path string. Questions on this? We showed this last time with open. Any questions on this code? Okay, so here we're going to take this stat buff, and is this a pointer to a stat buff, or is this a stat buff structure? It's a stat buff structure. It's allocated in memory. Who allocated this? Did we have to call malloc to allocate this? No, we didn't have to call malloc, right? Just like if I said int x, I didn't have to allocate 32 bits for that. This is a function local variable. We'll learn about this when we do compilers. But the compiler generates code that automatically allocates this for you. Okay, so now we have a stat buff struct already allocated. So how can we, okay, so the stat buff syscall requires a pointer to it. How can we get a pointer to this stat buff? What's that? Yeah, how do we do that in C? So we have this stat buff constructed. How do we get its address? So we can pass it to the stat syscall. Ampersand, yeah, ampersand. So if we want to get a pointer to this, so struct stat star, this means pointer to a stat struct. I'll just call it stat buff pointer. And you just use ampersand to get the address of something. Did anyone not learn about ampersand when learning about pointers? I think everyone learned this, right? So probably it was in a more kind of classroom abstract setting, but this is like one of the use cases of actually dealing with pointers is memory management stuff and dealing with the system. All right, so now we've got this pointer to our stat buffer which we created. Now this stat buffer is effectively empty, or depending on the compiler, it'll have garbage data. It'll have unexpected data in it. But now we have some value that's the same data type, struct stat star. So to do our syscall, we say stat, and then the path. So I read in the path from the user, so I'll just use this path variable. And then what's the second argument to this function? What's the variable? Do we have a variable for this? It's a pointer to a stat struct, right? Do we have one already available for us? Yeah, the one we just created. So stat buff pointer. And that's it. Are we done with this syscall? No, why? It returns a value, yeah. And what is that value that it returns? If you forget, remember you can look at the man page. On success, 0 is returned. On error, -1 is returned. So how can we do error checking for the stat call? Or let's just, if there is an error, let's just exit right away. How can we do that? What's that? Yeah, we can save it to an integer, so we can say like the stat ret val. And then how do we check whether we had an error or not? Yeah, we check if it's equal to -1. And if it is equal to -1, we had an error, so we can do the same trick, or the same kind of easy code, where we just use p-error to automatically print out an error message for us, and then exit. And I keep forgetting what the macro is. Oh, it's exit failure. So there's a predefined macro, so you don't have to remember the number, although the number is easier to remember than me. All right, there's our syscall for stat. So let's run this, make sure it actually works the way we expect. No errors. Ask for a path. All right, so we didn't have any errors. Let's check the error checking. Let's actually put a file that doesn't exist. And here's our p-error printout. This is printed out by pre-error. And notice that I could have put any text in p-error, and it'll just use that as the prefix to my error message. So I said stat message. And this is what p-error generates. It looks at that e-noent or that error code and generates a human readable message for it. All right, so we've actually successfully done our system call, or so it seems. So how do we get information out of this? How do we get some information about our file that we've just opened? Here's the documentation of the stat struct that the system returns. So let's say we wanted to figure out what the inode number was of this file. How could we print that information out? Any takers? How could we? What would we write if we want to use the stat system call to figure out what the inode number of this file is? Yeah, you would just print out this variable here. So this is a definition of the struct. So remember the struct, you just say struct stat, and then it's just filled with fields that each have their own data type. That's just a way to combine multiple variables into a single variable, into a single data structure that stores many variables. So yeah, we can just print out, I don't actually know what the I know T data structure is, or data type is. There's probably cleaner ways to do this than just printing it out as an integer. All right, but we've got this stat buff. So how do we print out this information? Which variable is this st I know field contained? Hey, what? Say again? In stat, like this? Dot. st I know. Okay, let's see what the compiler says. Okay, it's complaining. It's saying basically that this is not a struct. Stat is not a struct. So do we have any variable called stat here? No. There's a stat buff. And is stat buff a struct, or is it a pointer to a struct? So do we use dot or arrow? Dot, right? So it's stat buff st inode. Oh yeah, so it's complaining that I have the wrong data type for printing it out. And voila, we've printed out the inode number. We can see whether it actually matches the stat command, and it does. So here we've already successfully made a system call. We've used this low-level style of passing a pointer to a structure. The system call will populate data in that structure for us, and it'll, once the system call returns, it'll print that. We can access that information from user space. So just to kind of convince you that the system call is actually doing something, I'm going to, before stat call, after stat call. So you can see there's a value in this because we've allocated memory for this struct, but it has uninitialized data in this struct. once we make the syscall, the system will actually take a pointer to our structure and it'll overwrite memory and user space from kernel space. And one other point, we also have a pointer to our stat buff. So how can we dereference that struct? The arrow. So the arrow is equivalent, I think, if I can get this right, is equivalent to dereferencing and then doing dot. So saying arrow is the same thing, it's shorthand for first dereferencing and then using a dot to access the field. So let me make sure this actually works. And there we go. So all these system calls are equivalent to each other. Or all these prints are equivalent to each other because we're just dereferencing a pointer to the struct. Questions on that? I know that for some of you, they might be familiar with this. Some of this probably looks really nitty-gritty, low level. But yeah, this is why you learn about pointers in C to be able to do this kind of code like this and understand the nuts and bolts of it. Questions on this? Okay, so for numeric data, it's easy to use printf and the existing print formatting to print things out. But there are other data types here that are not numeric, or they're numeric, but interpreting them is kind of system dependent. So for instance, the file type and mode. This is all packed into a single field. So the file type here is not like text or a string or MP3 file. This is Unix system type, so directory file versus regular file versus device file. And the mode is its permissions, like read, write, execute. And you can see this is all packed into a single field. So you'll see this kind of coding style at low-level programming for kind of extreme efficiency. So instead of having multiple individual variables, one variable for read, one variable for write, the designers will pack these into a single field, a single bit vector, effectively. And getting out information from this kind of bit vector also requires some low-level C-style programming. So who's used like bit masking before? Bit-level operations. Okay, not many. Did they teach this in Intro to C? Okay, they did teach this. CS1. Okay, so everyone should have seen it. I guess everyone should have seen a little bit of this. But okay, and the documentation of this is, again, it's documented, it's in another place. You can actually see it here. So if you look at this ST mode, it tells you, see this man page for more information about how to get this information out. So if we want to find permission information or the file type, we need to look at this inode documentation. So this is like detailed documentation of every field in this stat buffer. So I'll just go down to ST mode. You can see here there are these bit masks. So if you bitwise and this field with this mask, you'll get out those few bits that represent, say, the file type. And these are the values you'll get. So you can see that these individual values, if you OR them all together, you get this mask, basically. Any questions on that? I don't want to go too much into like bit twiddling. It's pretty tedious to do. But if you look at, this is this entire, this entire number here represents all the values that the ST mode field can store, and you use this bit mask, you AND with this bit mask, only these numbers are going to be 1, only these binary numbers are going to be flipped on, and it'll turn everything else to 0, and then you can compare it to figure out which file type you have. And fortunately, they even give you a little code to show you how this works. So we take the buffer, the ST mode field from the buffer, and then what does this ampersand mean in C? We've got 2 ampersands here, right? What does this one mean? I think I heard AND. Yeah, this is bitwise. Yeah, go ahead. That's like the bitwise AND op. Yeah, that's what it does. So the bitwise AND operation will look one bit at a time and see if they're both on. And this is used. The trick that's being used here is to use this bitwise AND in order to store multiple values in the same number, in the same binary field. So by masking or bitwise ANDing this field with this mask, we'll pull out only these bits that represent the type field. Questions on this? Here's this. Does anyone want to see this illustrated at all? Oh, damn. Now I gotta do it. All right, so I'm assuming this is octal. All right, so I'm assuming what's going on here is each of these, 0, 1, 7, 0, 0, 0. I think these represent 3 bits each. I hope. Let me know if I get this completely wrong, but I'm pretty sure this represents 3 bits each. So each of these fields represents 3 bits. 1 is probably like this. What's the bit? What does the binary look like for 7? 1, 1, 1. And then it's all zeros all the rest of the way. So if the system the system tells you that this is, say, a regular file, what's the value for regular file? Well, it's 0.0000001. Let me I'll write this down for regular file. I think this is 7. So if you have a regular file, it's going to be all zeros the rest of the way. This is our mask. This is the value for a regular file. And so, so even though, this is the value of a regular file, these other values correspond to other information. Like this might be there might be bits here in other parts of let me make this clear. So if this is what you get for ST mode, if this is its value, 101, 001, 00010, some binary string, and this is our mask for I format, for the inode format. If we AND these two things together, what are we going to get if we AND them? So if I AND them together, what is the result going to look like? So we AND these together, 0 and 1 is 0, 0, 0 is 0, 0 and 1 is 0, 0, 0 is 0, 0, 0 is 0, and then 1, 1 is 1, and all the rest of these values are 0 because everything here is 0. These are 1s, but these are 3 are 0. And then this mask, everything is 0. So the rest of this is 0. Make sense? So this is what we're going to effectively get. I kind of hand waved a bit over this. But it's going to take this ST mode field, and it's effectively just going to carve out these 4 bits. And those 4 bits represent these types of files. So 7 files here, 4 bits. There's enough information to store these different types. And then once we've masked and we've pulled out just these 4 bits, we can compare the number against these predefined constant values to figure out whether this is a socket file, a symbolic link, regular file, block device, etc. Questions on that? Does it make sense, sort of? Okay, so here's the rest of the code for what that looks like. It was actually in our example here. I'm just going to do some more fancy stuff here. I'm going to use a switch statement. Here's us bit masking our ST mode field. And I have some predefined code here that will check for each of these values. So here you can see these correspond to our mask, the actual values of the file type field. And so I just print out a string that represents what type of file it is. Questions on that? Questions on that part? All right, so let's see. Hopefully I didn't make a mistake. Let's see what this looks like. So now you can see here, the file type here is a regular file. Now it doesn't matter whether this is a program or anything. If this is some file stored on disk, it's a regular file. But if I take, say, a device file, like this mem file, it says it's a character device. If I take, can I look at disks here? Say it's a block device, BLK. But yeah, so in this class we're really going to be dealing with regular files and directory files. Let me also show a directory file. And now it says directory file. All right, any questions on this? This is a very deep dive into some of the mechanics of using these system calls, but any questions so far on this? All right, let's go over some other system calls. They're a lot easier than this one. I'll guarantee you that. So let's look at reading and reading, writing, and reading and writing files. And I actually have all these created already. So let me just use the created ones. And walk through them. Okay, so read takes a file descriptor and a buffer and a count. Where do we get the file descriptor from? Open, yeah. So the return value of open is this file descriptor. And it's just a record that the system keeps of all the open files that you have. It's a pointer, effectively, to an open file. So if the open command works correctly, the open call works correctly, we get this file descriptor of the open file. And then we can use that for reading and writing to the file and other file operations, like stat. So here's what a read call looks like. We give it a file descriptor. We give it a buffer, which is, again, like stat, an already created, allocated string, or not a string, sorry, a byte array. And then the number of bytes to read. So why do we have to give the number of bytes to read in the C world? So let's say the file is 100 bytes, and we make a buffer that's 5 bytes long. What's going to happen if we do a read and we don't tell the system when to stop reading? You're going to have a buffer override, right? You're going to be writing into memory that's not allocated. Right? It's the classic C problem of buffer override and overread. I don't know what that was, but so just like anything in C, the arrays don't have any. They're not stored with any length of their string. So all the system calls that are dealing with these data structures either need to be a struct that has predefined size, or needs to be an array with a number telling you how much you've read. Okay, so just like with any syscall, we need to do error checking. If you look at the return value for this syscall, on error, -1 is returned. On success, the number of bytes read is returned and the file position is advanced. So one annoying part here, and this is why you have a C library, is that if this, it's not an error if this number is smaller than the number of bytes requested. So why might the read not return as many bytes as you asked for? So you have, a megabyte buffer that you've asked for, and you read in, you ask for a megabyte of data from the file. Why might you not get a megabyte of data?
Because this file is smaller.
Yeah, the file might be smaller. Or, and this is a subtlety in Unix programming, because read was interrupted. So the kernel may decide, or the kernel may need, to stop the system call and not actually give you all the data that's available in the file. So you may not even know whether you've read all of the data that you could possibly read. You'll have to restart the system call. So this is called this is called the PC losering problem. Kind of an offensive name, but. And I've linked to a article that describes this problem. You can find this in the notes, but it's an explicit design of Unix where if there's an error, or if there's if the kernel cannot give you all the data that you asked for, you as the user have to restart that call and keep running read until you get all the information that you asked for. So very, very manual. Yeah.
It'll pick up reading from where the signal, or where like it got interrupted.
Exactly, yeah, it'll pick right up from where it got interrupted. So you can see here, on success, number of bytes is returned, and the file position is advanced by this number. So internally, one thing that the file descriptor points to, one thing that the open file records, is where in the file you currently are. So if you ever use like seek, fseek, or lseek, you can change the position of that current pointer into the file. So this just allows you to keep issuing read commands, and you don't have to manually manage where you are in the file. You just keep saying read, and this pointer into the file will keep advancing for you. Okay, so we call the read system call, check for errors, and here we're just going to print out the return value of read, which is the number of bytes that was read, and print out what those actual bytes were. Here I also print out buff size and to compare the two. So let's look at an example of running this. So I'm going to make a file that has let's make a file that has a lot of text in it. So we've got 24 characters in this file. If I read in, only 10 bytes to this, and I try to print out the 10, let me actually comment out the rest of this because this is only going to make things more confusing. So I've only asked for 10 bytes, so I get the first 10 bytes, HELLO, new line character, WORL. So that's the first 10 bytes of the file, right? If I have a file that is smaller, it only has 3 bytes in it, then I'm only going to read those, well, 3 bytes plus the new line character. I'm only going to read those 4 bytes, and my buffer is just not going to be completely filled. So if we print out the rest of that buffer, what do you think we're going to see when I run this on small? I only read in 4 bytes, 6 bytes left in the buffer. What's going to be printed out when I try to print out the rest of that buffer? Well, just garbage data, whatever data was in memory at the time when you allocated this buffer here. All right, questions on read, the interface to read? So the consequence of this is if you're writing, say, a copy function, if you want to copy the contents of one file to another file or print it out, you need to first of all know, how large the file is that you want to read. Or you need to make a buffer, a small buffer that's smaller than the file, and just keep reading over and over and over in a loop until you can't read any more of the file. All right, questions on read, file read? All right, let's look at file writing. Okay, so file writing, in the same vein, the system will only write either as much of the buffer that you give it, or it could be interrupted, just like with read, and not actually write everything that you requested. So just like read, it takes a file descriptor, it takes a buffer, and the number of bytes that you'd like to write from that buffer. And it tries to write all of those bytes to the file. But for various reasons, you may not actually get all that written. So if you don't have enough space, you'll get an error for that. Or just like with read, if it was interrupted, if the kernel needed to stop that syscall to handle something else, then you may not get all the bytes written. So this requires a little complexity in trying to actually make sure you even have a single buffer being written to the file. So this is why you have like fopen and fread and fwrite, because just writing to a file itself already requires kind of slightly complicated code. All right, so let me walk you through what this code looks like. So this program will take in two strings. It'll take in the path you want to write, and it'll take in a string to write to that file. This is getting the length of the string. This is going to keep track of how much we've written so far, because we may not be able to write all of it in one system call. And in a loop, we're going to write over and over and over. We're going to call the write call until we get everything written to our file. So let me diagram what this looks like briefly. So let's say we want to write hello W, and our buffer is only, say, 2 bytes, or only writing 2 at a time. So we have this variable message, which starts out pointing to the first character in our buffer. And we call the write command. Let's say we call the write command for all 6 bytes, but it only gives us 2 of the bytes. So we call write to our file. We write message. And we ask to write 6 bytes. Let's say it only returns 2. Well, we've only written these 2 files so far, or these two lines so far, or these 2 bytes so far. So what this code will do is it'll keep track of total written and add it to our pointer. So now, if total written is 2, then message will be updated the next time we call to start printing here at L. And so here we only need to write 4 bytes. So we ask it to write 4 bytes. Let's say the system only gives us 1 byte. Then we'll add that. So this is write C is the return value of this. We'll add this to total written, and we'll update message to start writing here inside the string. So we've written this. And if in our last call we ask for 3 bytes to be written, if we get all 3 bytes written, then we've written the entire buffer to our file. Does that sort of make sense? The behavior of this function? Now maybe the first time you call write, you get the entire buffer written to your file. But because the system is not guaranteed to write the entire buffer, we have to keep track of the difference between what we asked it to write. So we asked it to write message C minus total written. The first time this is run, this is the length of the message minus 0, so it's just the length of the message. But we have to compare that to what was actually written. So if we asked for 6 bytes to be written and only 2 bytes were written, then we need to call write again. And so this loop is just a clever way to call write as many times as we need to in order to get this entire message written to the file. Questions on that? Let's see this actually working. All right, so file write takes a path and a string like hello. And I'd have to make it a very, very long string in order to get it to write in many, many executions. But if it were ever interrupted or we ran out of space, this would fail if it ran out of space. But if it couldn't write the entire thing the entire time, then it would call write multiple times with this code. All right, questions on this system call? Okay, let's leave it at that for today. Homework is up. And next time we'll look at start processes. I'll explain the file system project and we'll look at processes. All right, everyone, have a good week.